Oh yes, I told you this project was important. My CNC chainsaw is gonna save the day.
Stay back, I will kill you.
So it's obviously not a real bear trapped in the log, it's the idea of a bear. And my CNC chainsaw will remove everything that isn't the bear. Although normally the log is wood, not foam. We'll get to that. If you're wondering why I'm trying to cut bears out of logs with chainsaws, this is something that people do. And I could even buy one, but they are really expensive. And I knew in my heart that I could make a much worse one for free. I just need thousands of dollars in equipment. This is one of those ideas that's so bad it wraps back around to good. I think you know what I mean, right? So the basic idea here is I'm attaching a custom chainsaw to the end of a robotic arm. So I should be able to move it anywhere that I want and cut whatever I want. The arm is a Tormach ZA6. They asked me if I'd be interested in beta testing it, and there really is only one answer to that kind of question. I live streamed the setup to my Patreon, although I tried to do it without a manual, which was kind of a mistake. I'm sure my CNC chainsawing feature requests have been invaluable. Robot arms are super cool. They can move and rotate any way. See how the joints are moving in crazy ways to make it go in a straight line? The math behind this is called inverse kinematics, and for once, I don't have to solve it. Thank goodness. So to understand CNC chainsaws, you first have to understand a few things about normal CNC machines. I'm sure you've seen a CNC machine run. You put a block of metal in, you hit a button, it goes to town, and you get a nice part when it's done. Have you ever wondered how it knows where to cut? The answer is it doesn't. It doesn't know anything. The only thing that a CNC machine knows how to do is follow instructions. For example, I might tell it to go up, maybe a bit higher, and then down again, to the left, to the right, and so on. If I tell it to stab itself in the face, it'll do it. To make the machine cut this part out, I have to tell it the specific moves that I needed to do so that the resulting shape is the part that I want. The motions that you tell a CNC machine to do, they're called tool paths because they're the path that the tool takes. When I want to make a part, I load it into special software that generates the instructions for the machine for me. I'll tell it things like drill a hole here or cut a pocket here, and then the software will generate thousands and thousands of specific instructions for the machine to follow to make my part. Just like the CNC machine, the robot arm doesn't know anything. So I'm gonna have to write software to tell it specifically how to move so that the chainsaw cuts out the part that I want. This is one of those things where it's pretty easy for a human to figure out, like, duh, just cut it here, but it's very hard for a computer to figure out. It's kind of like a CAPTCHA.
Dog.
It says /.
These kinds of problems are hard because a computer doesn't see like a human sees. It doesn't have a concept of shape or space. It can do things like tell me how much material would be inside of a specific cut. This leads to a kind of guessing game where you test all the different possibilities and choose the best one. This is similar to trying to guess a password. The number of combinations of all the different letters is really high. For example, a 5-letter password has about 12 million combinations. It is completely infeasible to go through all these possibilities to find the best or even a really good cut. I'm going to start by focusing on just removing most of the material and not worrying too much about the shape of the part. I'm going to do it in a very inefficient way, but it'll allow me to avoid most of the problems I just described. I'm going to use what I call the apple peeler algorithm. Have you ever seen one of these old-timey apple peeler/slicers? If you haven't, they are a miracle of science. The interesting thing about this apple peeler is how it removes the apple from the core. It essentially does one long continuous spiral slice. I can do something very similar with the chainsaw. If this was my log, I could cut down to the depth of the part that I want and then rotate around, changing my depth to whatever I need to just hit the part that I want. And then just repeat that all the way down the part. This would remove most of the material. To actually do the apple peeler algorithm, I start with my part, and this is a side view. I take a bunch of cross sections of this part that are spaced out by the thickness of the chainsaw blade. Let's say one of the cross sections looks like this. My goal is to go all the way around this layer and cut away everything that isn't the model. If I do that for every single slice, then it'll remove almost all the material. The downside is we convert almost the entire log to sawdust. But it's easy, and that's what matters. There are a couple problems. The first is that the robot arm can't actually reach all the way around a big part. I'm going to put the part on an automatic turntable so I can turn it to face the chainsaw. There is another problem. If I cut along this surface, the chainsaw is too big to fit into this zone. I also can't fit the chainsaw into this area here. There's an amazing math trick that I've been wanting to show for a long time, so let me show you. I take the shape of the bar of the chainsaw and I mirror it. I place a copy of it at every single point along this curve. The shape formed by the outer edge of all of these copies is all of the valid spots that I can move this and it won't go into the places that it can't go in. There's a rigorous definition of this. It's called a Minkowski difference, but it basically is magic. If we put all this together, we can calculate the chainsaw motions to cut a part out. I want to try my toolpaths, but I need a chainsaw that sticks out the absolute minimum distance. The further the saw sticks out, the more it will multiply any error in the positioning of the robot. And then on top of that, it will multiply the forces going back into the robot, which can overload it. Think about it like a wrench. The longer the handle is, the more torque you can put for the same amount of force. And that's why I have this bar, which they call a cheater. When you have a bolt that's really stuck, you get way out here and snap your wrench in half. Ideally, just the blade would be sticking out. But I can't just bolt a chainsaw to the side of the robot like this. These arms move in mysterious ways, and many of these movements will make the saw collide with the robot. All right, here's my design. It's built around a pole saw, which is basically a chainsaw on a stick, which you use to cut branches out of trees and stuff like that. The number one concern for this design is keeping it as compact as possible so that it sticks out the minimum amount. The way my pole saw works is there's a shaft going into the back of it, and if you turn the shaft, that drives the blade. I'm driving the pole saw through this belt, which allows me to fold the motor up next to the pole saw and make it a lot more compact. This motor is an electric skateboard motor, so it's almost an electric skateboard. This design should be able to avoid hitting the robot arm at least most of the time. All right, let's get this thing built. Remember, this is my software-only project. Don't pay any attention to what I'm doing here. It occurred to me how dangerous this thing is. It has a kill radius of like 1.5 meters, and it can really zip around. All right, it's pretty safe now. I really just want to go for it, but some tests on a small log seem smart. Oh, finally. I really wish I would have built and tested the chainsaw before spending an entire week writing the apple peeler algorithm. I thought it would be all right based on my big chainsaw, but it is just way too slow. I estimate from the speed that it was cutting that it would take about 10 hours to remove most of the log, and there's zero chance that that little chainsaw would survive continuous cutting for 10 hours. Now that we've established that converting the entire log to sawdust isn't a great strategy, I need to find a way to calculate a series of cuts that removes as much material as possible. Although this is where it gets tricky. If I'm only allowed to take slices off the model, then there'll be no way for me to get into these concave areas. The best I'll be able to do is something like this. In computational geometry, this is referred to as a convex hull. That's no good. I want my bear to have curves. What I really want is for the chainsaw to take scoops out of the part. Chainsaws can't do this. They can't turn. They can only keep cutting in the direction that they're cutting in. So the best thing that I can do, come in and cut and then come back out, and then come in from another angle and meet the other cut, and then this will remove a sort of a wedge shape. Unfortunately, throwing wedges into the mix makes choosing a good cut about 1,000,000 times harder. Now I have to think about where the cut is, but how wide it is and how long it is. I'm not going to go through all the math, but my conservative estimate for the number of possibilities is approximately 1 bazillion. It would probably take my computer 1,000 years just to count them. So what I need is a way to search through this massive number of possibilities and find my needle in a haystack. I'm going to try a computational trick called gradient ascent. Imagine I have a little ball and I'm trying to get it to the top of this peak. I could move the ball to every single point on this map and then figure out which one is the highest, but that's really inefficient because I have to check so many points. The idea behind gradient ascent is that I start with a guess, and then I say, if I move the ball side to side, does that make me go up or down? And if I move the ball in the other direction, what does that make me do? And from this, I can figure out what direction will make the ball go up the steepest path. So you move up some, and then you repeat it, and you do it again and again. And in very few steps, the ball will walk up the hill and get to the peak. I can do the same thing for my cutting problem. I can start with a guess and see how much material that cut would remove. And then I can figure out how much the removed material would change if I tweak the cut. In doing this for all the possible changes, I can figure out the direction that will most improve the cut. This method sounds really good, but the devil's really in the details. I've spent more than a week on this, and I cannot get it to work. The problem with gradient ascent is that it can get stuck at points that aren't actually the highest point. You can imagine that if my guess was here, I would walk up to this point, and then the ball would happily say, I'm at the highest point, but it's really a false summit. Getting stuck at a false summit happened to my program almost every time. I'm sure there's someone really smart out there who could make this work, but I can't. So this means I'm gonna basically have to write it again using a different technique. Hopefully third time is the charm, because I don't know how much more of this I can take. I'm a little weary of writing code, so I'm gonna go work on some other problems. There's a very subtle problem that I have to deal with. If I don't fix it, my parts are gonna look completely wrong. This stand was made by a total poser amateur welder. This means squareness is unlikely, which is a bigger issue than you probably think. Imagine that I'm trying to cut this part out with the chainsaw, and the chainsaw can move around the part to cut it from any direction. The robot thinks that up is up. Now imagine that this part is tilted, and this part hasn't been cut yet, so it's just a block. So the chainsaw is going to try to cut this dotted area. It doesn't know that the part is tilted. It'll just miss the part. Where things get really bad is when you start rotating this part that you're cutting. So what will happen is the chainsaw might cut too shallow over here. Then if you rotate that part that you just cut 180 degrees, then you bring the chainsaw over here, it's gonna cut way too deep, and it's just gonna completely destroy your part. Getting your rotation axis lined up with the chainsaw is extremely important. Everything is adjustable, and I made a calibration system so that I can measure this and then dial everything in. I could fix this in software, but I'm pretty sure I would do it wrong the first time, so this is just easier. For machines like this that can kill you and not even realize that they killed you, the e-stop is really important. It's what you slam if anything is going wrong and everything stops. Although the way I originally designed this, there was two e-stops. There's an e-stop that I made that would cut the power to the chainsaw, and there was an e-stop built into the robot that would stop it. I found this a bit concerning. If the robot is coming at me, I have to decide which e-stop I'm gonna hit. I found a way to wire my button up so that it stops the chainsaw and the robot. I press this whenever I'm gonna go into the kill box and disables everything. I have the warning sticker and I have the e-stops, but I still feel like it would be really easy for this thing to kill me. And so I wired in this party/warning light, and whenever the system is in kill mode, it will enable this, and it's a nice visual indicator that you will die if you come in here. I think it's time to get back to the software. So before everyone tells me, I know that a rapidly exploring random tree is probably the way to go here. If you don't know what that is, it's just a way of searching an enormous number of possibilities to find a pretty good solution. From my perspective, this would be a terrible solution because I would have to write a lot more code. And besides, I have a half-baked solution that has a chance of working. Imagine that this is my part and this is the remaining material that I need to cut away. I start by taking every point along the boundary of the material I need to cut, and I calculate how far it is to the closest point on the model and what direction I need to go to get there. I use this to find the furthest point from the model, and then I search along this direction to figure out the biggest cut that I can take. I'll explain how that works in a second. This method works pretty well, but it does have a big problem. If I search at this location right here, I could very easily end up searching in this direction or in this direction. And when I look at this, I think I would want to do a cut kind of like this so that I really get into that notch. So what you can do is you can search in this area. What are the possible directions I could go in this area? Then you can search for that range of angles and pick up these special cases. So when I say I search along a direction, let me tell you what that means. Imagine that I'm trying to find the best possible cut along this path to the part. My simple algorithm starts here, and it figures out what's the widest angle cut that it can do. It tests all the way up to the part and chooses the best one. Doing exactly what I just described is probably still too slow, but it's not too bad to write, so let's try it anyway. All right, this is probably gonna take a while. I have a very unexpected problem, which is that I cannot find a good 3D model of a bear to cut. I thought there's gonna be tons of these things. There's just tons of bears in the T-pose, which would be hilarious to carve out of a log, but they just don't really fit the aesthetic that I'm going for. So I found this dog model, Don't let the low poly count fool you. It doesn't matter. I'm cutting this with a chainsaw. All right, it's been a while. Let's see if the algorithm's done. This is way too slow. This will take a week or two to process. Thankfully, we have an ace up our sleeve called software optimization. This means using tricks to make your code go faster, make it really hard to read, and usually break it. So my plan is to take advantage of what's physically happening, like what these computations actually represent in reality, and I'm going to use that to cut out a lot of computation that I don't have to do. We can know from the geometry that some things may or may not happen without testing them. For example, if I run a test at this point and I find that this is the widest wedge that I can cut, I know that any angle less than this will also work because it's inside of the bigger angle. I also know that any point on this trajectory before this one is also good at that angle because they're also contained within it. By doing this single test, I eliminate an enormous amount of variables that I don't have to test anymore. I can do similar tricks when I figure out how long the wedge cut should be, as well as what orientation it should be at. I was just really excited because my optimized code ran in less than a millisecond, and then I realized that I optimized it so hard that it didn't actually compute anything. I fixed my dumb problem and it is a lot faster. It's maybe about 10 minutes to generate the cuts for model, whereas before it was days and weeks and months, so solid improvement. Everything that I've described so far is to compute a single cut. To compute all the cuts, I just do that routine over and over. And when it's done, I have a set of moves that the chainsaw needs to do to cut out my model. All right, I need some big logs. Fortunately, I know a guy with a tree. This log looked a lot smaller outside. All right, here we go. The other purpose of the stop is to stop the robot before it does something stupid that I told it to do. All right, here we go. For some reason, the chainsaw is getting hot, like really hot. If I try to cut into the log so that the tip is going into the log, it just won't cut. I think what's happening is that the blades on the tip just aren't cutting, they're rubbing. This is why I was smoking so bad and setting off my smoke alarm. I think the problem might be related to this little anti-kickback tooth. There's no way that I'm gonna be able to cut this log, at least not today. With some really big changes in my toolpaths to maybe rock the saw or something like that, I might be able to get through it, but that completely breaks everything that I did. We'll save that for a future project or something. For now, I'm just gonna do the reasonable thing and compromise. This is basically a log, right? If you think I'm just gonna hit go and it's gonna work, you are sorely mistaken. In fact, let me show you my 5 easy steps to wasting an entire week. Start by going up to the machine full of youthful optimism. Then hit the start button. Within 5 seconds, smash the e-stop. Go upstairs and fix whatever boneheaded programming error you made. And then go back to step 1. And for a bit of variety, hit the robot with the chainsaw several times. Ideally, this would be violent enough that you have to rebuild the whole saw, at least 4 times. But look on the bright side, there is a finite number of ways to screw it up, so you will eventually finish. This doesn't exactly look like a dog, but it doesn't totally not look like a dog either. I think I need to go figure out what the heck is going on, but it's something. A lot of testing later, I caught the perpetrator red-handed, and it was me. Previously on Stuff Made Here. Getting your rotation axis lined up with the chainsaw is extremely important. Long story short, I screwed up the alignment. Nothing lined up, so I was pretty much just skewering the poor dog randomly. It should be fixed now, although that's what I said before. I'm almost out of things I can screw up, so I'm feeling pretty good about this one.
Stay back, I will kill you.
Finally! This was a long time coming, but it is so cool. Overall, I'm really happy with how this turned out. My heart says make a wooden dog, but my brain says, but think of all the other things you can do with this arm. I'm torn. This is way better than I was expecting, especially based on the last result. There were some areas that it just couldn't reach, and so it's not cut there. And then there's some cuts where it couldn't make the connecting cut, so there's a few slices just into the model. I'm super curious to see what my wife thinks of this. I think she's really gonna like it. She likes dogs. But before I get to that, I want to talk about this video's sponsor. If you can take just a minute to check it out, it really helps me out and I would really appreciate it. This video is sponsored by KiwiCo. What KiwiCo does is they send you a crate every month with everything that you need to build an entire project. And I've talked a lot about growing up and making things and why, honestly, KiwiCo is phenomenal. My wife also grew up making things, so I thought it'd be interesting to hear from her instead of me for once. It's in the box.
Ah, electroluminescent sculptures.
In this crate, you bend EL wire to make really cool sculptures. When I saw this, I knew my wife would love it. That's one of the cool things about these crates is that there's so many different types. Like, I think this one you're gonna like. So you probably noticed that I like engineering. My wife is totally different, which is one of the reasons I love her so much. She really is into the arts. It was fun to watch her do this crate because it was something that she really enjoys. Ooh.
Oh, it's so cute.
Whatever your kid's age or interest might be, there probably is a KiwiCo crate that they're gonna love. So go to kiwico.com/stuffmadehere. You'll get 50% off your first crate, and I've put a link down in the description. I really do recommend it. I think just within our immediate family, there's probably been like 10 crates given and received.
I had fun with this.
Yeah, she's gonna go
make another one.
She's gonna go make another one.
It's so cute.
You like my dog?
I love it.
Where should we put it?
On a column like those lions. You should make one in wood. And
yeah, I try. I think it looks a lot better than the first dog.
well, yeah, that looks like a weird mountain that someone would call Monkey Rock or something, because it sort of looks like a monkey a little bit. You should put the crown on the dog.
Ah. This project was really fun, and if you enjoyed it, please consider subscribing. It helps me out a lot, and it'll keep you in the loop when I post new projects, so win-win.
Win.
Oh, wait, the final question. So we both made dogs. Whose dog is better?
That really is a hard one, actually.
If it's so hard, why does this dog have a crown on?